In the previous video, we talked about diagonalizable systems, systems of the form y prime equals a times y, where the matrix A is diagonalizable. Now I'd like to talk about non-diagonalizable systems. These are systems of the form y prime equals a times y, where the matrix A is not diagonalizable. And I'm going to start with an upper triangular system. So here we're going to look at an example. It's y prime equals the matrix 2, 0, 0, 0, 4, 1, and 0, 0, 4. And this matrix is upper triangular, but it's also not diagonalizable. Okay, it's nearly diagonal, but with this one here that actually prevents you from being able to diagonalize this matrix. What that means, of course, is that there are repeated eigenvalues. So maybe we should make that point here. There are repeated eigenvalues. Okay, lambda is 2, 4, and 4. And there's an eigenvector that corresponds to lambda equals 2. And there's an eigenvector that corresponds to lambda equals 4. But there is no eigenvector to correspond to the second repeated eigenvalue of lambda equals 4. So there's only two linearly independent eigenvectors for this particular matrix. So what we'd like to do is to solve this upper triangular system using techniques that we already know. So I want to rewrite this system in kind of a fun way. Okay, so I'm going to rewrite this using each component. So y1 prime is actually going to equal just 2 times y1. And y2 prime in this case then equals 4 times y2 plus y3. And y3 prime, in fact, equals 4 times y3. And so because this system is upper triangular, not all of the equations depend on each other. And so we can actually solve some of these equations. Okay, so we have y1 prime equals 2 times y1, which tells me that y1 is equal to a constant, we'll call it c1, e to the 2 times t. Now, y3 prime is equal to 4 times y3. And so it depends only on y3. And so y3 prime is actually equal to c3, we'll call that constant, e to the 4t. So the last equation that we have is y2 prime is equal to 4y2 plus y3. But y3, in fact, we already said is c3 e to the 4t. So here I'm noting that this is actually the solution y3. So we're going to actually plug that in there. I'm going to rewrite this in a more familiar way. We're going to write this as y2 prime minus 4y2 is equal to c3 e to the 4t. And the way that you can solve this linear differential equation is you can find a homogeneous solution and then find a particular solution. So we're going to do the homogeneous problem first. Homogeneous problem is y2 prime minus 4y2 is equal to 0. And so y2 we can think of as being c2 e to the 4 times t. And now we want to find a particular solution. Now this is the method that we used when we were solving second order differential equations that were linear, but this actually works for any nth order linear differential equation. Okay, so our particular solution, we're going to have to make a guess. Okay, so our particular solution, we'll call it y sub p. Okay? And we want to make it look like the form of the right-hand side of our equation. So we want to make it look like this. So we might write a e to the 4t, a constant times e to the 4t. But hopefully you realize that e to the 4t is already part of the homogeneous solution. So we can't just write a e to the 4t. Okay, instead we're going to have to write a times t e to the 4t. Then we want to plug that back into our differential equation. So we are going to need to know what the derivative of that is. The derivative of a t e to the 4t is in fact a times 1 plus 4t times e to the 4t. I will leave that to you to find that derivative and then simplify it in that way. Okay, so now I'm going to plug this back into my non-homogeneous problem. So I want to know what is yp prime minus 4yp. And that, in fact, is going to be, yp prime is going to be a e to the 4t plus 4a t e to the 4t, so that's yp prime, minus 4yp, so minus 4a t e to the 4t. And of course, when I'm done, I want to set that equal to c3 e to the 4t. So you'll see that this cancels with that. And then you'll notice that the e to the 4t here matches the e to the 4t there. So it must be that a is equal to c3. Okay, so my solution, y2 of t, which I probably shouldn't have called that one y2, I should have probably called that one yh for the homogeneous solution. Okay, my solution is going to be c2 e to the 4t plus a, in this case, is c3 t e to the 4t. Okay, and now I can write down the full solution to this problem. The full solution to this problem I'm going to call y of capital Y of t. And that's going to equal c1 e to the 2t, c2 e to the 4t plus c3 t e to the 4t, and then finally c3 e to the 4t. And so this is kind of a nice technique that you can use to solve a upper triangular non-diagonalizable system.